Let's take a closer look at one particular kind of continuous random distribution, which is called the uniform distribution. As the name implies, the probability for any value to randomly come up is the same as any other value. So let's go ahead and draw the graph of this function. So here I have an x and an f of an x plane, and a uniform distribution is going to involve 4 values. First, we'll look at values c and d, which represent the upper and lower limits that the x variable could possibly take. And let's go ahead and draw this function. The way this function is going to work is it goes along 0 to the lower limit, comes up here, over here, down here, and back along 0. And this value being c, this value being d, we can now write out the function. And this is going to be a piecewise function, and it is going to take the form of 1 over d minus c for the range that x can take, or 0 otherwise, as we've graphed on our graph. So anytime that we want to express a range of probability on this function, this will involve 2 more values, which we're going to label as a and b. So if I'm looking at a uniform distribution function that can range from c to d, and I want to calculate what is the probability that a randomly selected value from that distribution would fall between a and b, it's going to look like this. So the probability function here will look like this. And key to understanding what's going on here and being able to successfully solve a problem like this is to understand what this ratio is telling us. Because the nature of this distribution is that it always forms a rectangular curve shape, then a certain percentage or proportion of area will always be the percentage of area of interest that we're solving for divided by 100% of the total area. So if we're able to put unit values on all 4 of these values, we can then readily solve for the probability. In just a moment, we'll look at a couple sample exercise problems for that. Let's go ahead and jot down here the mean of this uniform distribution. And for a mean, that tells us that we just take the maximum value, add it to the minimum value, and divide by 2. So a simple average of the min-max value. And for the standard deviation of this uniform distribution, we're looking at the maximum value minus the minimum value divided by the square root of 12. Let's take a look at a sample problem. Alright, for our first exercise problem, let's go ahead and read the question. Here we're told that Delta Airlines quotes a flight time of 2 hours and 5 minutes for its flights from Cincinnati to Tampa. Suppose that we believe that actual flight times are uniformly distributed between 2 hours and 2 hours 20 minutes. And we'll just look down here to part A, which asks us to show the graph of the function for the actual flight time. So let's go ahead and do that. The function will take on a shape of a rectangle, x, f of x. The lowest possible value, we're told, is 2 hours. So let's go ahead and we'll think of that in minutes, 120 minutes. And the maximum flight time is 2 hours 20 minutes, or 140 minutes. And to draw this function out, it corresponds to the 0 here, goes up here, over, down, and back along 0. So the f of x value for this is 1 divided by d minus c, in this case 1 divided by 20. So here we have a f of x equals to 1/20th. And that takes care of part A. Let's look at part B. Here they're asking, what is the probability that the flight will be no more than 5 minutes late based on the quoted flight time? So our first task here is to put a specific numeric value on the x value that we're working with. So in words, what we're looking at is no more than 5 minutes late. So no more than 5 minutes late. And if we look up at the flight time that's quoted, which is 2 hours and 5 minutes, that will convert to 125 minutes. So therefore, an on-time flight would be 125 minutes. A flight that is 5 minutes late would be 130 minutes. And to convert that to a probability statement, the key word here is no more than. So therefore, this is going to be the probability that x would take a value less than or equal to 130. And let's go ahead and draw that graph out. I always recommend drawing the situation that you're working with to help you understand it. Here we'll just draw the rectangle itself. Lower boundary value is 120, upper boundary value is 140. The specific x value that I'm solving for now is 130, and I'm interested in all of the area that falls to the left of or less than or equal to 130. So I'm going to shade this area in. And if we use the A minus B format here, then we'll have B minus A and D minus C. So in this case, B will be 130. A corresponds to our lower limit, 120, and D minus C represents the entire unit width of the 100% of the rectangle, and that will be 140 minus 120, which is equal to 10 out of 20, and that's equal to exactly 50%. All right, good work. Let's move on to part C, where they're asking us what is the probability that the flight will be no more than 10 minutes late. Or reading the question correctly, what is the probability that the flight will be more than 10 minutes late? So let's go ahead and sketch that out first of all. So 120, 140, and in this case, the value that I'm solving for corresponds to the x value that would represent the limit of being more than 10 minutes late. And in this case, 125 would be 0 minutes late, so therefore 125 plus 10 minutes would be 135 minutes, and therefore that's my x value that I want to solve for. So probability that x is more than, greater than, or equal to 135. Let me go ahead and draw that on my distribution here, and greater than indicates 135 and higher up to the maximum value. So rather than using the A, B, C, and D formula method here, let's see if we can solve this one visually. So we're always going to be working with the ratio here, and that ratio will be the number of units of interest to us for the solution as the numerator, and the number of units that represents the entire width of the rectangle as the denominator. Our entire rectangle is 20 units wide, and the area that we're interested in describing is 140 minus 135, or 5 units wide. So therefore, the answer to part C is the probability that the flight will be more than 10 minutes late is 25%. And finally, part D asks us to solve for the expected flight time. So let's go ahead and solve for that. And expected flight time is comparable to the mean of this uniform distribution, and as you recall from the previous video, that is solved by C plus D divided by 2, or the average of the upper and lower endpoints. So in this case, 140 plus 120 divided by 2, 260 divided by 2, and the answer for that is 130. Intuitively, 130 is the value that is halfway between 120 and 140. 10 units are on the left, 10 units are on the right. And although not asked by the question, let's go ahead and solve for this standard deviation as well. The formula for that is D minus C divided by square root of 12. So 140 minus 120, and square root of 12 is approximately 3.46. Therefore 20 divided by 4.46 gives us a standard deviation of approximately 5.78. Thanks for watching.